One of the concepts in our course is hypothesis testing and how to use resampling and permutation test to facilitate hypothesis testing. So there are lots of questions and there is a lot of confusion, especially about hypothesis testing and how we employ resampling and permutation tests to compute or to perform hypothesis testing. So what I will do here is we'll take the same example. We'll take the same example that we discuss in the course, and I'll explain the same example in more detail now, stressing on the points, stressing on the points that most students forget, because the flow of arguments that we often do in hypothesis testing is very easy to miss out the details. So I will stress on the key points so that most of the questions that are asked on this topic are easily solved by just viewing or by redoing the same example, by stressing on the key points where people miss out or people do not pay enough attention to, right? So the first step first, okay, let's first see what is the setting like. So we have two classrooms of students, classroom 1 and classroom 2, right? We have taken 50 observations. We have taken 50 observations of students in class 1, and we have taken 50 observations of students in class 2, right? So this is already observation. This is already an observation or a set of observations that we have already made. Remember, we already made these observations. We already made these observations and collected this data of 50 students from class 1 and 50 students from class 2, right? This is the empirical or the actual data. This is the actual data that is collected, right? Now, once you collect this data, right? So if you compute the mean of all the students in class 1, let's call it mu1. Let's take the mean of all the students in class 2. Let's call it mu2, right? So these two are also, you can compute mu1 as the average value or the mean value of all the students in the 50 students that you have sampled from class 1. Mu2 is the sample mean of all the students in class 2, right? Now I will define a variable called x, which is mu2 minus mu1, right? Remember, mu1 and mu2 are computed from the actual observations, right? So in the video, we call this as x, or we call this as capital delta, right? So whether I refer to it as capital delta or x, it's basically the difference between the observed. Remember, I'm using the word observed. The observed means or observed sample means of students, 50 students in class 2 and 50 students in class 1, right? Now let's assume this value is 10 centimeters. Now the very key important thing here is this is an observed value. This is an observation, because we got this value of capital delta or x from a series of observations, right? This observation has already been made. Now, right, this is very important. We call this as step 0 of hypothesis testing. Okay, just to keep track of the steps and the flow of arguments. So first, we have already made this observation. Of course, instead of 50, if I can take larger samples, yes, I'll get more rigorous data, but that's okay. So my sample size here my sample size is 50, because I've taken 50 observations of students in class 1 and 50 observations of students in class 2. There could be more students. The population of class 1 may be 500. The population of class 2 may be 300. But I'm just taking a sample here. And this, what we get here, is basically the difference of sample means of class 2 and class 1. And this is an observation. This is a ground truth. This is a truth, because we already made this observation, because this is computed from real actual data. Let's not forget that fact, right? Number one. Number two, now once I get this observation, or once I make this observation, the next question I'm going to ask is, what is the probability? The question, this is very important. What is the probability of observing a value of x which is greater than equal to 10 centimeters if there was no difference in actual class heights. in class heights. Now let's break this up into pieces. It's very, very important to break it up into pieces. Okay. So now what we are saying here is, remember, we already made the observation here. We already made the observation of 10 centimeters. Now the question we are asking is, imagine if there was no difference in class heights. If there was no height difference in class heights, if there is a big if here, if there was no difference in class heights, what is the probability of still observing a difference of 10 centimeters between sample means when sample size equals to 50? So I'll repeat it again. Very, very important. This is what we compute as our p-value, right? What is the probability? What is the probability of observing a value of greater than 10 centimeters, making this observation, right? What is the probability of making this observation? Remember, we already made an observation which is exactly equal to 10 centimeters. Now I'm asking, what is the probability of making an observation? And what is your observation? Your observation is when you take sample sizes of 50 each, and when you take the sample means, and when you subtract the mean of class 2, the sample 2 from sample 1, if you get, what is the probability of getting that value? So I'll repeat it. What is the probability of getting a difference of greater than 10 centimeters for sample means of class 2 and class 1 when the sample size equals to 50, right? We are writing that whole thing as just this because of the way we defined x. What is x here? X is the difference of sample means when sample sizes equals to 50, right? So what is the probability of making this observation if given, or if we have a hypothesis that we are making? And what is that hypothesis? This hypothesis is that there is no difference in class heights, right? So what are we doing? We are computing the probability of making this observation given, or if this is given, right? So probability of x greater than equal to 10 centimeters given a hypothesis. This hypothesis is that there is no difference in class heights, and this hypothesis is called the null hypothesis. This is what we compute, and we take this and we call this as the p-value, right? It's very, very important. That's why I've written it in English very carefully. P-value is, for this specific example, p-value is the probability of observing a sample mean between class 2 and class 1, difference of sample means, which is mu2 minus mu1, when the sample size is fixed to 50, right? What is the probability that that difference or that variable or that statistic, this is called the test statistic. This is called the test statistic. What is the probability that your test statistic is greater than 10 centimeters? And remember, this is coming from an observation. So what is the probability of the observation given a null hypothesis, or given that there is no difference in class heights? This is what is your p-value. Now let's assume, this is a very important piece of argument. Like if p-value is small, so let's say p-value is equal to 0.01 or 1%, right? By small, what I mean by this is, it means less than 5%. And you might wonder, why are we taking less than 5%? Because this is customary. We typically take less than 5% as a customary value. So if p-value is small, what happens? Let's go through the flow. What does it mean if p-value is small? If p-value is small, let's write it mathematically. It means that the probability of x greater than equal to 10 centimeters given h0 is small, or it is 1%. Now, right, this is what it means, right? Because this is the definition of p-value. This is what p-value means. If p-value is equal to 0.01 or 1% or small, what does it mean? It means this probability, this exact probability is small. Now, here comes the fun fact. Here, from this, what can I perceive? Here, see, if this is small, then your x, but while this is small, we already observed that x equals to say 10 centimeters, or we observed that x is greater than equal to 10 centimeters, because if it is equal to, it's also same as greater than equal to. We already made that observation. Don't forget that fact. The very first observation we made was that x, or capital delta, is equal to 10 centimeters. So I've already made this observation, which means this is true. This part is true. this part is an observation, or this is certainly true because it comes from an observation. If this is true and if this probability is small, right? So this part is true, this part is true because it is coming from an observation. But this probability, this overall probability is small. Then what does that imply? Because there are only two parts in this probability. There is either this part or this part, right? So this part is absolutely true because that's an observation we made. We already made this observation, so it can't be incorrect, right? Given this observation, now if this value is small, then what does it entail? What this implies that because we have already made this observation, this implies that H0 is less probable. H0 is less probable, or in other words, H0 may not be true. May not be true, which means we reject our null hypothesis. Okay, I'll go through the flow of arguments. It's very, very important to get through the flow of arguments. Okay, first of all, if p-value is small, like 1%, we typically take anything less than 5%. It's customary in statistics that if anything is less than or equal to 5%, we consider it small. Then you might say, why 5%? It's customary. 5% is considered small enough. Of course, there are cases where we'll use less than 1% or less than 2% or less than 5% or less than 3%. Depends on. Typically, it's customary to take a value of less than 5% to be small. Now, what does it mean when I say p-value is small? It means this whole probability is small. Probability of x greater than equal to 10 centimeters given the null hypothesis is small. Now, if this is small, there are two components here. There is either this part or this part. Now, this part is certainly true because we already made the observation. What did we do in step 0? We actually made the observation of 10 centimeters, which means this part is certainly true because in x greater than equal to 10 centimeters, there is also equal to, and this is our observation, which means x greater than equal to 10 centimeters is certainly true. And that's the only observation we have. Now, between these two, if this is certainly true because we already made the observation, what might go wrong? Then why is this probability small? This probability is small because this must be less probable, or this must be incorrect, or this must not be true, or this may not be true. So this implies, because this overall probability is small, this implies that our H0 is less probable or H0 may not be true. If H0 is not true, then we reject H0. What does rejecting H0 mean? Rejecting H0 means that our hypothesis that there is no difference in class heights is incorrect, which means there is actually a difference in class heights, right? And by the way, for this whole analysis, for this whole thought process, we only have these 100 points. That's very important. For this whole analysis, to perform this whole analysis, including computing, you might wonder, how do we compute p-value? I'll come to that in a while. That's done using permutation test and resampling. We'll come to that in a while. But in this whole process, the only thing that we have are these 100 observations, right? 50 samples from class 1 and 50 samples from class 2. That's all we have. We don't have anything else yet, right? Now, just by basing on these 100 observations, we have successfully concluded that there is no difference in class heights. Very, very interesting idea in statistics. Just by using these 100 sample points, we have made a huge leap, right? And we concluded using the whole hypothesis testing paradigm that there is no difference in class heights. Now there comes the question. So the flow of arguments is very important. Oftentimes what students forget is that this observation is a ground truth. Students forget that, right? That's why I've stressed it a lot here. This part is the core of hypothesis testing and p-values, right? This is an observation that's already made, right? And the whole probability being small basically means that this must be improbable or less probable or maybe not true, which means we should reject it and take the alternative hypothesis, which is nothing but the opposite of H0. Now comes the interesting question. How do we compute our p-value? So what is our p-value in a nutshell? Our p-value is probability of x greater than equal to 10 centimeters given H0. This is what we have to compute, right? Now remember, to compute this whole thing, we just have our class 1 and class 2 samples. We have 50 samples of class 1 and we have 50 samples of class 2. That's all we have. We don't have anything else. Using just these 100 values, we have to compute this probability. And we do that using the ideas from resampling and permutation test. Right? So I'll take you through step by step again. Now the first step here is, since we have class 1, right? We have class 1 and class 2. Right? We have 50 values in class 1 and we have 50 values in class 2. Now given these 250 values, what do I have to compute? I have to compute probability of x greater than equal to 10 centimeters given h0. And what is x here? X is nothing but mu2 minus mu1 when the sample sizes are 50-50 each. But remember, I can't again sample them from classes. The only data I have is this 50-50. I can't again sample from the classes for whatever reason. Given just these 100 values, how do I compute it? That's what your permutation test and resampling helps you answer. First thing they say is this. You have 100 values. Let's combine all the values here and create a large set called S, which has this 100 values, right? Imagine if my null hypothesis was true. What does my null hypothesis being true mean? It means there is no difference in class heights, right? What do you have to compute? We have to compute probability of x greater than equal to 0, or in other words, probability of mu2 minus mu1 greater than equal to 10 centimeters given h0, which means I somehow need to now simulate. Remember, I somehow have to simulate the null hypothesis. I somehow have to simulate the null hypothesis just using these 100 values. I don't have anything else. All I have is just these 100 values. And using these 100 values, I need to simulate my null hypothesis. And what is the null hypothesis? Null hypothesis is that there is no difference in class heights. So if I take this large set of 100 values, wherein I have taken all the values from the class 1 and class 2, just the heights. Let's assume there are 50 observations here and 50 observations. I combine all of them and I jumble it up. Right? Now I get 100 observations. Now if I break them randomly, now if I sample 50 randomly from here and 50 randomly from here, there will be some heights in this from class 1. There will be some heights from this from class 2. Similarly in this set, so I'm randomly splitting this 100 into 2 sets. Right? Let's call this set S1 and S2. Right? Let's call this set S1 and S2. Right? Now when I randomly split it, there will be some points here in this set from class 1. There will be some points from class 2. Similarly, there will be some points here, roughly 50% of points here from class 1 and 50% of points from class 2. Roughly, because of randomization. Now if I compute the average of all the heights in class 1, in this sample 1, average of all the heights in this sample 2, and if I do mu2, if I perform mu2 minus mu1, let's assume I get a value which is delta 1, small delta 1. Now remember, what is this delta 1? This delta 1 is basically mu2 minus mu1. It is the, again, I'll repeat it. I'll read it in English. It is the difference of sample means. Remember, it is the difference of sample means when my sample sizes are 50, right? And when I assumed that there is no difference in class heights. See, to simulate this no difference in class heights, we are taking this random sample. That logical step is very important. How do you now simulate H0? To simulate H0, I'm saying take the 50 students here and take the 50 students here, put them into a large bucket of 100 students. Now randomly pick 50 students here, 50 students here. When you randomly pick 50 students and 50 students from the pool of 100 students, there is going to be no difference in class heights because you have randomly picked it. This randomly picking 50 and 50 here is a way to simulate your null hypothesis, right? So your delta 1 is basically a simulated difference in class heights, right? With sample size equal to 50 and with null hypothesis equals to true. And why am I saying null hypothesis is true? Because I've randomly picked. By randomly picking, I'm ensuring that there is no difference in class heights, isn't it? By randomly picking, I'm ensuring that this randomization or resampling is the key, especially for this given problem. Now, just the way I have randomly split it into two sets S1 and S2, and I computed delta 1, I can redo this whole randomization multiple times. If I redo it, and I get a set S1, S2 again, which means I get mu1, mu2 again, and if I take this difference between them, I can get delta 2 again. If I just repeat this randomization once more, because this is trivial to do in a computer. If you're given 100 points, I can split it into two sets of 50-50 points randomly by using a simple coin toss, right? So if I compute lots of these delta 1, delta 2, delta 3, so on and so forth, let's assume delta 10k or 10,000. So I'm performing this simulation 10,000 times. And what is each of these values? Each of these delta i's are simulated differences in class heights with a sample size of 50, and while simulating with your null hypothesis being true, right? So I've computed 10,000 simulated values. These are all simulated x's. Because what is x? X is mu2 minus mu1. So these are simulated x's, simulated differences with h0 being true. Which h0 being true. Now if I sort them, all these values may not be sorted, right? If I sort them, and let's assume I get delta 1, 2, delta 2 dash, delta 3 dash, so on, delta 10k dash, sorry. These are, I just sort them. Because these are simulated values, what do I want to compute now? I want to compute probability of x greater than or equal to 10 centimeters given h0, or in other words, I want to compute probability of, okay, because what is each of them? Each of them is an x. So what is the probability of your delta i's that you have computed? Because what is each of them? Each of them is a simulated x, right? So amongst all of them, if I sort them such that, if I sort them in increasing order, right, I've sorted them in increasing order. Let's assume my 10 centimeter value is here. Let's assume my 10 centimeter value is here, which we call as a capital delta in our videos. Let's assume my 10 centimeter value is here. And let's assume there are 2k values here and there are 8k values here. Then what does it mean? It means that when I simulate, it means here, look at this. I've simulated h0. I've assumed that h0 is true. And what is each of my x? Each of my deltas is a simulated value of x. And of all the deltas that I simulated, of all the 10,000 deltas I've simulated, or 10,000 x's that I simulated, 2,000 of them are greater than or equal to 10 centimeters. Right? So this is equal to 2,000 or 2k. Of how many simulations? Of 10k simulations. So this is 20%. If there are 2k values here, remember these are all in increasing order. So this is less than equal to, 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 so on and so forth. So there are 2,000 values of x's that are greater than 10 centimeters, because what is x? Each of your delta i's are simulations of capital X. Remember, that's what I wrote here, right? Each of your delta i's are simulated xi's with null hypothesis being true. So which means, what does this mean? It means 20% of your deltas, or 20% of the times whenever your null hypothesis is true, 20% of the times, right, you observe a height difference of greater than or equal to 10 centimeters with a sample size of 50. Don't forget the sample size of 50. Now if this value, so now let's do it again. Now I have delta 1 dash, let's say delta 2 dash, delta 3 dash, so on and so forth, delta 10k dash. Now if my 10 centimeters lies here, and if I have only, let's say I have total of 10,000 points, right? Right? If I have only 100 points here, right? The rest of the 9,900 points are here. Then my probability of x greater than or equal to 10 centimeters given h0 equals to 100 by 10k, which is equal to 1%. This is my p-value, right? What I'm computing here is my p-value. When my p-value is small, again, let's go back to the previous argument that we saw. If my p-value is small, then I reject my null hypothesis. If my p-value is not small, let's look at this, right? Here my p-value is not small. P-value is not small. P-value is not small. Hence, we do not reject H0, we accept H0 here. Right? So there are two parts to this argument. First part that you have to really get it. The very first part is what is hypothesis testing, which I've explained in the first part. You have made an observation. This observation is the ground truth. It's absolutely true. Given the observation, now you're trying to build this probability that you want to compute. Right? Now, if that probability or p-value is small, then you reject your null hypothesis, or else you accept it. Now, how to compute that p-value is what you do using resampling and permutation testing, right? And for this, we do all of this. And remember, in this whole exercise, all you have is the 50 samples from class 1 and 50 samples from class 2. That's all you have. You don't have anything else more than this. It's very, very important to understand that. Now, the other typical question that comes up is, how do you design what is the null hypothesis? We pick the null hypothesis which is easier to simulate, which is easier and possible to simulate. Because remember, in the permutation testing, you have to simulate H0. So some people ask, why did we choose that there is no class difference as the null hypothesis? What if I chose my null hypothesis as having a class difference? Then the challenge here is, how do you do the simulation? The actual problem, the actual challenge in designing hypothesis tests, in designing a hypothesis testing is to design what is the test statistic, which is like our X, to design what is our H0. This is non-trivial parts. These are the problem. So when you have to design a hypothesis testing, you have to design what is the test statistic, you design what is the null hypothesis, and you have to design how to simulate the null hypothesis. So you'll choose that null hypothesis which is easier to simulate. If your null hypothesis is hard to simulate or impossible to simulate, you can't go ahead with hypothesis testing using permutation test and resampling, right? So actually designing a hypothesis test is non-trivial. You need to really get into the groove and understand how to design the right test statistic, how to design the right null hypothesis, and how to design the right simulation. Because if you mess up any of them, then you can't compute your p-value. If you can't compute your p-value, your whole hypothesis testing goes for a toss, right? So lot of questions that are typically asked for resampling and permutation testing, or for p-values, or for hypothesis testing. I hope I've covered all of them in this half an hour long video, where I've revisited, focusing mostly or stressing mostly on those areas which people overlook and get confused with hypothesis testing and resampling and permutation test.